Some problems are just simple. But then there are others that look simple, but they're hiding this whole universe of complexity. So in this explainer, we're going to dive into that universe, and we're going to discover something really beautiful: the wisdom of knowing when it's time to stop searching for that one perfect answer. Okay, let's kick things off with a question that feels super simple. Imagine you're planning a road trip, and you've got a bunch of different cities you want to visit. What's the shortest possible route that hits every single one of them and gets you back home? I mean, sounds like a piece of cake for a computer, right? And this isn't just a hypothetical. This is a classic real-world problem. Think about a delivery company trying to save money on gas and time. All they want to do is figure out that one perfect order of stops to make the total trip as short as possible. The idea itself is simple, but as we're about to find out, the solution is anything but. So, to really get why that seemingly simple delivery route is so incredibly tricky, we've got to look at how computer scientists actually think about problems. See, they have this whole system for classifying them, and it turns out there's this massive, massive gap between what they call easy problems and what they call hard ones. All right, first up, let's talk about the easy ones. In computer science, these belong to a class called P. Now, P stands for polynomial time, which is just a fancy way of saying that as the problem gets bigger, the time it takes to solve it grows in a predictable, manageable way. Think about sorting a list of names. The more names you add, the longer it takes, but it doesn't suddenly explode into an impossible task. These are the kinds of problems computers just chew through. Okay, next up is a class called NP. And this is where things get really interesting. Now, a lot of people think NP means not polynomial or not easy, but that's not it at all. The key idea here is that for NP problems, if someone just gives you a possible answer, you can check if it's correct really, really fast. The classic example is a Sudoku puzzle, right? Solving one can take forever, but if I hand you a finished puzzle, you can tell me if it's a valid solution in like a minute. That's the heart of NP. Fast to check, even if it's hard to solve. And this actually makes perfect sense. I mean, if a problem is easy to solve in the first place, well, then it's got to be easy to check too, right? You just solve it again and see if you get the same answer. That's why you see this here. The easy P problems are just a small circle inside that much bigger circle of NP problems. And all of this leads us to what is probably the single biggest, most famous unsolved question in all of computer science. It's literally $1 million prize question. Does P equal NP? In other words, if a solution is easy to check, does that automatically mean it's also easy to find? Is creating a masterpiece just as easy as recognizing one? The answer is, we have no idea. Nobody on the planet knows for sure. Just let that sink in for a second. A question that sounds so simple, is finding as easy as checking, is one of the deepest mysteries in all of mathematics and computer science. Okay, so what's really wild is that inside that big NP circle, there's this special group of problems. You can think of it as the hardest of the hard club. These are called the NP-complete problems, and they have this absolutely wild, almost magical property: they're all connected. If you could somehow find a fast, efficient solution for just one of them, it would be like finding a master key. You would instantly unlock a fast solution for every single one of them, all at the same time. So this diagram kind of helps put it all together. See that intersection? That's NP-complete. These problems are the toughest of the tough. To get in the club, a problem has to be two things. One, it has to be an NP, so you can check an answer quickly. And two, it has to be NP-hard, which just means it's at least as hard as any other problem in NP. They're basically the certified heavyweight champions of hard problems. And this club isn't small. It has thousands of members that pop up all over the place. Remember our delivery truck puzzle? That's the famous traveling salesman problem, and it's a card-carrying member. So is trying to satisfy a complex logical formula or finding the best way to lay out a computer chip. I mean, these aren't just weird abstract puzzles. They're at the very heart of logistics, AI, biology, you name it. It's kind of mind-blowing when you think about it, that all of these incredibly different, complex problems might actually just be the exact same puzzle, just wearing a different disguise. Okay, so if finding a perfect, fast solution to these problems is basically impossible, then what are we supposed to do? Well, we do what smart engineers have always done. We cheat. Or, more accurately, we change the goal. And this quote just nails the shift in thinking. Instead of beating your head against a wall for years trying to find the perfect solution, which might not even be possible, The really smart move is to spend your time building an algorithm that gives you a good solution and does it fast.
And this is it. This is the cheat code we were talking about. It's called an approximation algorithm, and the idea is just brilliant. You make a conscious choice to stop looking for the absolute 100% perfect answer. Instead, you design a fast algorithm that gives you an answer you can prove is really, really close to perfect. It's a trade-off, right? You give up a little bit of perfection to gain a whole lot of speed and practicality.
But, how good is good enough? Well, we actually have a way to measure that. It's called an approximation ratio, and it's basically a quality guarantee. So if we have an algorithm for a delivery truck with a ratio of, say, 1.5, that means we have a mathematical promise that the route it spits out will never be more than 50% longer than the absolute best possible route. We might not know what the perfect route is, but we know for a fact that we're close.
And here's what that looks like in math terms. The point is, this isn't just guesswork. We're not just, throwing darts and hoping one lands near the bullseye. This is a rigorous, mathematical way to find a great solution and to prove exactly how great it is. It really is a huge shift in perspective. Maybe perfection isn't about hitting that tiny, exact bullseye every single time, especially if it takes a million years to aim. Maybe the real elegance, the real perfection, is knowing you can hit the inner scoring ring every single time without even blinking.
And that really brings us to the biggest takeaway from all of this. Understanding NP completeness, it isn't about giving up. Not at all. It's about gaining this incredibly important piece of wisdom that every problem solver needs. At the end of the day, this is why this stuff matters so much. It literally saves brilliant people from wasting years, or even their whole careers, chasing an impossible goal. When you realize a problem is NP complete, it's like a giant friendly signpost that says, hey, stop. The perfect answer is that way, and it's a dead end. Your real genius lies in finding a clever shortcut. So we've totally flipped our original question on its head. We started out asking, how do I find the absolute best route? But we've learned that a much, much more powerful question is, how do I find a great route right now? It's all about shifting from chasing some theoretical ideal to achieving what's practically best. And you know what? That's a question that goes way beyond just computer programming. In our projects, in our work, even just in our daily lives, we all run into these ridiculously complex problems. So maybe the real wisdom here is learning to pause and ask ourselves, when is the best solution the only one that'll work? And when is a really smart, proven good enough actually the most perfect answer of all?